we are in the lecture 10 already. So in lecture 9, we have considered the Laplace equation in two-dimensional structure. But you can easily guess that the main motivation of our introduction for two-dimensional Laplace equation is just to prepare the Poisson equation in the same dimensionality. So that is our eventual goal. So one-dimensional and two-dimensional introduce big differences in its treatment. So we have considered many issues in two-dimensional structure in the previous lecture, lecture 9. Now our discussion on Poisson equation today will be quite brief, and I will just leave my homework to you for your main milestone. Why don't you just go to the two-dimensional Poisson equation. When you talk about the Poisson equation in two-dimensional space, and if we explicitly write down the equation, it looks like this. Compared with the previous Laplacian equation, it was something like this. So phi plus phi equal to 0. So you can easily understand there occurs non-zero, in general non-zero source term, and also we can have position dependent coefficients in front of the first derivatives. In rigorous sense, this is not the Poisson equation, but we all understand that this is just a name called for this equation, generalized Poisson equation. If we have a look at this Poisson equation in this form, it would be quite complicated. However, you know that if we introduce the form we prefer to have, something like this, then we can easily introduce small volume integration over control volume. Then we can get full working code. So simply speaking, we just make a surface integral over our control volume, and its flux and infinitesimal area component should be calculated. And since the surface is just made of several planes, so we can easily consider each of them. Okay, so that is not that difficult, and I will not repeat it again because we have already done it in many times. And let's go to the second part, boundary condition. Fortunately, in the case of boundary conditions, we have no difference from the Laplace equation. It is the same. Yes, so you don't have to worry about that. So the only thing I wanted to add in the discussion of Poisson equation is initial gas. So initial gas is the starting gas solution for our Newton-Raphson method. Eventually, we will solve many different bias voltages, starting from, for example, gate voltage equal to 0.0 volt, and we can, for example, increase it by 0.1 volt and 0.2 volt. We will continue this procedure until eventually we reach at the target voltage, for example, 1.1 volt. That will be our typical procedure. So in every case, for example, if we are working with a 0.5 volt, then how can you provide initial gas for this bias voltage? It is not that difficult because we have previously solved 0.4 volt and it was successful. And this successful solution will be used as the initial guess for our next bias point. So, in order to solve 0.5 volt, we need 0.4 volt. Then for 0.4 volt, we need 0.3 volt. If we just repeat this procedure, then we are reaching at the initial, the origin of all this chain. So that will be, for example, 0.0 volt. In order to provide the initial guess for 0.0 volt, what is the appropriate value of initial guess? Okay, maybe you can ask me, oh, we can go to minus 0.1 volt, but that does not make a solution. So then what will we do if we can go to a negative and negative voltages? Anyhow, we have to close this loop. So I wanted to ask you the way of terminating this chain of initial guess. For other voltages, we can rely on our previous voltage, which seems to be more easier to get the solution. However, anyhow, at a certain voltage, we should be able to calculate the initial solution. So that is my concern. Then we have a rule of thumb. This is not a strict law or the golden rule. However, in reality, every device simulator is using this rule. I will introduce this rule from now on. So in this case, we have to decompose into our system into two pieces depending on the material. For example, if we have insulator regions, then we have to consider this part. And if we have semiconductor regions, then we have to consider them separately. So for insulator regions, usually we just leave it 0. It means that usually we don't care about it, just leave it 0. Actually, the converged solution for even at Vg equal to 0 volt will be highly deviated from this 0. So this is quite a poor strategy. However, we just apply silicon regions. We have to apply the local charge balance. So what is the local charge balance? Simply speaking, at a given position R, we have to have the balance between the positively charged quantities like positively charged dopant and hole density, and this is a positively charged one, and negatively charged one, that will be the electron density, should be balanced. That is local charge density. Of course, at equilibrium in the semiconductor device, usually local equilibrium is not a valid condition for equilibrium system, because there we can have a certain depletion layer. So in the depletion layer, we can have a strong electric field and charge unbalance. However, even when we understand this charge unbalance inside our system, but we have no idea actually to solve that problem without help of our numerical simulation. So our second choice is just to apply local charge balance, although it is not the perfect way to cure this problem. Okay, once we accept this local charge balance, although it is not perfectly valid, After that, just to apply the expression for hole and electron, which is given by Ni times exponential phi over Vt. Of course, here we have minus, and Ni exponential plus phi over Vt. You know it. Then we can easily follow this equation. Okay, so, and you can remember that you have already solved this problem. So yes, it was homework number 7, and at the time when we discussed about Newton-Raphson method, that was used as an example. So if you have solved it correctly, then you can just reuse it for your homework number 10 before starting your simulation. First, for every point inside your semiconductor region, please solve this equation. Either Newton-Raphson method, or you can also follow your analytic solution. No matter how you solve it, it doesn't matter. So you can anyway get the correct solution under the assumption of local charge balance. Of course, when you start the full Newton iteration for your Poisson equation, since this is not the correct solution, this is far away from your correct solution, you will have certain deviation and certain errors at the early stage of your calculation. But Newton-Raphson method is quite robust, although the provided initial guess is not the perfect one, but anyway you will be able to get the solution. You know, this Poisson equation, especially in this nonlinear Poisson equation with the expressions of this hole density and this electron density, is known to be most robust in our lecture course. So, I mean that this equation, nonlinear Poisson equation, is anyhow well behaving equation. So you can get the solution. Let me just announce our homework today a little earlier. So compared with our previous lectures, I just announced it a little earlier because this is the right place for me to announce it. So due is next Monday, so you have 5 days, but I strongly recommend you to start it now. Means that this is not trivial problem. So compared with your homework number 9, I said that is a trivial problem. But you know, this homework number 10 is not trivial at all, and you may have many difficulties in solving this problem. So I strongly recommend you once again to start now. And this is the problem. So calculate the electrostatic potential at low gate bias and high gate bias. Of course, you cannot directly jump into 1.1 volt. That will not be successful. So in order to reach at your target voltage 1.1 volt, you have to introduce intermediate bias conditions. So that is understood. I will just explain the model system you have to solve. Now we have in total 30 nanometer. So this is 30 nanometer long system, and we can divide it into 3 pieces, 3 equal length pieces, and this part here we have source region, and this is drain region, and at the center we have channel region. And in this case, in this source region or drain region, we have highly n-doped regions. So 10 to the 20 per cubic centimeter, 10 to the 20 per cubic centimeter in n-type dopant. So you will have so many electrons inside it and almost no hole inside it. And in this part, this channel region, assume intrinsic channel. You have no doping inside your system. Okay, and this is 10 nanometer long, and this is also 10 nanometer long, and this is also 10 nanometer long. So this is a description along the channel direction. Okay, in this case maybe x direction, and we can go to the vertical direction. In vertical direction, you can find that the oxide thickness is 1 nanometer, and bottom one has also 1 nanometer thick oxide, and here we have 5 nanometer thick silicon layer. Okay, already you have solved this type of system quite often, so I think that you are quite familiar with this particular structure, but now you have to expand it along x direction, so have very large structure. So then let me just explain now the contact conditions. In this case, please use the work function you have used up to now, and for this gate contact also the same. You can just use the same one, and boundary condition for this source contact and drain contact, please apply the local charge balance equation. So simply speaking, just to solve this equation for these boundary nodes, and when you solve this local charge balance equation, then you will get electrostatic potential. From this one, you can evaluate both electron density and hole density. So assume that your electrostatic potential is set to be just phi naught, which is obtained from the local charge balance relation. So even for this drain nodes, you can apply the same values. In my opinion, actually, first of all, you have to build a Laplace solver for this system. That will be the first thing you have to do. I mean that previously you had a very small size system, like just 9 points and 5 points, and you have just 45 points, and yeah, now you have a much larger system, and however, anyhow, you can just expand it and set the boundary conditions. For example, this would be around 0.33 approximately volt, and you can also find certain values for this one. That will be also about 0.56 volt around. So this number will be found. So by assuming these correct boundary values and just neglecting any charge inside it, so let's say you solve just source free Poisson equation, then first you can try to solve it. So my recommendation is first build a source-free Poisson equation solver. So that is, as you know, that is just a one-shot problem. You can just solve it and see whether your system can yield a correct answer. Since this is around 0.5 and since it is just 0.33, so you will have slightly larger values here, slightly smaller values here, and you will have a smooth transition from 0.5 to 0.3. So please check this source-free Poisson equation first, and once you get the correct image for this source-free Poisson equation, then later just turn on your charge terms inside your silicon area. Then you will get the working nonlinear Poisson solver for this system. However, even in the case where you solve your source-free Poisson equation correctly, when you introduce charge terms inside your system, then it becomes a nonlinear equation, and you will have you may or may not, but probably may have many implementational issues. So that's the reason why I'm strongly suggesting to start your implementation today. This is quite an important one. If you can solve it, then this is really big deal. You have already solved nonlinear Poisson solver in one-dimensional structure. That is also a big deal, but this is even bigger thing. I mean that our goal is to build the full nonlinear Poisson solver for two-dimensional structures. Even when you have done our all homeworks quite well. However, I'm afraid that homework number 10 can be particularly difficult to most of you. So therefore, I just suggested to first implement source-free Poisson equation solver. So why am I suggesting in this way? So problem is eventually we wanted to make it so the nonlinear Poisson solver, but unfortunately this nonlinear Poisson solver has many ways to be corrupted. You can just make it worse in various means, especially when you introduce Newton-Raphson method and at any point you made certain mistakes, then that will just ruin your code. So once everything goes quite badly, then the usual response of a student under these circumstances is just to give up. Oh, I cannot solve it. I tried many times, but it just diverges, so I cannot go any further. So in order to prevent such a unfortunate situation, I just recommend you to divide your jobs into two parts. One is source-free Poisson equation solver. In this case, since you have no charge inside it, so this is just a linear system, and this linear system can be easily calculated. So if you have problem even in this source-free Poisson equation solver, then the first thing you have to do is just to improve it. So improve this source-free Poisson equation will be much easier than improving your nonlinear Poisson equation solver. So once after you have a working source-free Poisson equation solver, then at least you can find that your Jacobian matrix and residual vector and its update are well established. So then you understand when you expand your source-free Poisson equation to nonlinear Poisson equation, now you have to introduce certain things. Certain things is just charge terms inside your system. So I mean that when you just work without source term, your code works. And when you just introduce your charge terms, then your nonlinear Poisson equation does not work. Then you can confine your problem into only charge terms. Then if you have some certain problem, then you can just try to find out your bugs in your charge term. When you insert your charge term, if you have a problem, then my recommendation is even introduce the intermediate step. So in this case, instead of having the full nonlinear Poisson solver, first consider only doping densities. Then your solution will look quite bad. However, anyhow, this is just a linear solver, and you can find that your implementation for setting the doping density inside your system is well established and implemented. Only after that you can go to the full system. When you really start the implementation, you may find many difficulties you never experienced during your previous homework. So previous homework had a well-established examples, so you can follow it, and yeah, there was not that much difficulties. But in homework number 10, although every ingredient of homework 10 was explained myself step-by-step manner, but collecting them all and have a working code is not that difficult from my own experience. So I once again and again, strongly recommend you start today. So even in that case, you may have certain difficulties. We have about slightly more than 15 minutes. Then just discuss about our three-dimensional infinite potential well problem. The contents is already well explained in our preview lecture, lecture 9.5. So let me just quickly go to this one. You have a three-dimensional infinite potential well problem. So if you come from the physics department, you have already solved it quite many times. Among many possible 3D infinite potential well, we are now currently assuming that only LZ, the z directional size of our box, is particularly small. So our Lx and Ly, both of them are much larger than Lz. So typical number we assume in this case is this can be just 5 nanometer, or the thickness of our assumed silicon body. And Lx, that can be any number, but for example 100 nanometer, that is much larger than 5 nanometer. So in this case we can say the quantum confinement actually occurs only along this z direction. So along x direction or along y direction, we can just treat it as free electron. So x and y, we can just treat it as a free electron. For while in this example, we just consider a confined electron. I will try to solve this three-dimensional Schrödinger equation numerically. Usually they don't. I mean that they means that the researchers in computational microelectronics, they feel that this is useless. I mean that since we have really large scale and large scale, then we can treat it as a certain means and just to concentrate on the most important confinement direction. Okay, so here you have the solution, and the wave function can be decomposed into x directional one, y directional one, and z directional one, and eigenenergy can be given as a sum of x directional component, y directional component, and z directional component, and each of them x directional wave function and x directional eigenenergy just follow that of one-dimensional infinite potential well. So you can easily find the similarity. And one thing I wanted to show you here is now we are assuming the directional mass. So that is a little bit different. So we are now assuming the directional mass. In this case, for example, mzz can be quite large, so close to last mass, electron last mass, and this one can be quite small, just 1/5 of electron last mass. So if we just draw EQ energy surface of our electron, we having such kind of directional mass, then we can just visualize it as a ellipsoid. That here this is axis like kx, ky, and kz. Then it has a long direction, so with a heavy mass, and two other short direction corresponding to a light mass. You can understand this one. So why do we consider this kind of band structure? Because this is the typical band structure of silicon conduction band. Silicon conduction band has this type of isosurface, so we are now assuming that this kind of directional electron mass. So of course, this is just a slightly modified version of effective mass approximation. This is not correct in rigorous sense. We have to introduce a better Hamiltonian to get the solution. So usually people do have many different approaches to describe the Hamiltonian. The first thing we can consider is the effective mass approximation we have used and we will use during the entire course, but other choices are listed in here. Effective mass approximation, that is the simplest and easiest and not that accurate one, and we can define K.P method. So this is a slightly more computationally heavy, but still that much heavy, and greatly improve the description, especially for holes. In silicon material, the hole band structure is quite notorious to have complicated structure, but that can be well described by our K.P model. After that, we can also think about tight binding model. Tight binding model has been used quite a long time, almost about 20 years in computational microliths part as the most advanced Hamiltonian model for atomistic structure. However, in recent days, so about, can I say, within 10 years, so we now solve the Dft Hamiltonian. So Dft Hamiltonian is extracted from the Dft calculation for a given supercell. After that, that Hamiltonian is just used without modification. There are many different hierarchies of having Hamiltonian in the computational microelectronics course, but we are at the beginner position, so we will not talk about much of these advanced systems. So we will just use just the simplest one. So effective mass Hamiltonian 1. Once you have sufficient experience on effective mass Hamiltonian, so from my own experience, expanding it to a higher model is not that difficult. This is more or less a matter of your computational capability or your computational skill. So therefore, for a while, actually in this semester, we will just stick to effective mass approximation. Once you have energy state, then you can just count them. So here you have energy, and there can be many different levels coming from this triplet. So L, M, N triplet determines your energy. And when you have this U of energy state, then you can count the number of occupied state when you have certain Fermi level. For example, let's assume that this is really your system and your Fermi level is given here. Then at 0 Kelvin, then how many states are occupied? Then you can easily say 1, 2, 3, 4. 4 of them are fully occupied, and 1, 2, 3, they are not occupied. Then here we have 4. However, since we are considering spin degenerate system, so then we can say in this system, in total, 8 states are fully occupied. So this is the case of 0 Kelvin. However, if we go to 300 Kelvin, things should be a little different, because this lower energy part is not affected by this temperature. However, the occupancy of this state which is closest to Fermi level or closest to the Fermi level can be differed. Previously, at 0 temperature, 0 Kelvin, it was just 1 and 0, but we can now have a slight deviation from 1 and slight deviation from 0. That is described in the Fermi-Dirac distribution, and you know it quite well. So once you have the energy level out of your analytic solution for three-dimensional infinite potential wave problem, then by applying your Fermi-Dirac distribution under the assumption of 0 Fermi level, actually we have to have here minus EF to be more general. However, under our assumption Fermi level is regarded as the reference. So in this case, we can just count it. So here we have MATLAB example, and you can just follow it and you can find the total number. But what I wanted to ask you in your just exercise, just to follow this example and a little bit change it with your different Fermi level. Instead of Fermi level fixed to 0 electron volt, please try to evaluate. For example, your Fermi level is 0.1 electron volt, or for example minus 0.1 electron volt. What will happen? Of course, you will have more electrons and less electrons when you change your Fermi level. Okay, although we have 4 minutes left, but I think that this is the time to wrap up. So in the second part of our lecture 10, I just quickly moved on to the end of our lecture because everything was already well covered in the previous lecture, lecture 9.5. See you next Monday. Bye.